Right, everyone, I have made some new questions which are really similar to the questions that you have to complete by the end of today's session. So hopefully these will just give you a hand if you're struggling a little bit. I know some people got back to me and said that it was a little bit tricky, and that's fine. That's why I put the session over 2 lessons rather than just the one, because I know some people haven't quite finished it yet. Likewise, for the people that did hand in and the people that have submitted their work, if you want to unsubmit and then redo it or have another go or improve any of your answers or anything, then that's fine. Just do that in the session and then get these questions done. This is just really similar questions that I've just made and printed out. So I'm going to have a go. I'm going to solve these. I'm going to show you guys how to do them. It might be that I stutter and I stammer and that I get stuck, but that's because I'm literally doing this in real time. I've not practiced these at all yet. So got my calculator, got everything I need, and yeah, I'm just going to do it and hopefully we'll figure it out together. So start with question 1. It says, the half-life of thallium-201 is 73.1 hours. If a sample of thallium-201 has an original activity of 400 BQ, what will its activity be after 292.4 hours? Okay, so I'm going to write my activity in the middle. So the thing I want you to pay attention to is how I'm setting out each question, what bits of information I'm going to take from this. So I think what I'm going to do actually is I'm going to get my highlighter and I'm just going to pick out any key bits of information. So the fact that it's told me half-life 73.1 hours, it's got an original activity of 400 BQ, and they want to know what it is after 292.4 hours. Okay, so they're like the 3 key things that I'm going to need to do this. So I'm going to start out by writing out the original activity in the middle, and then I'm going to half this. So I'm going to do the first half. So we know that because it's a half-life, it means that half of the radioactive nuclei are going to decay. So it's going to become 200, half it again, 100, 50, 25, and then obviously I can go on further if I want to. Now, I'm just writing these numbers in just to start with. I don't know how far through this chain I'm going to go, but by writing it in, at least I can see what it's halving to. Okay, so I'm going to go up to there, I'm going to stop, and then I'm going to start filling my numbers in. All right, so this first arrow represents 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Okay, and I'm going to write the numbers in across the top of the half-life. So this first half-life is 73.1 hours. So 2 half-lives, this is extremely lazy, but I can't be bothered writing this in. That's 146.2 hours. And then I'm going to add on another 73.1. That's 219.3. I'm going to add on another 73.1. And I've got, oh look, 292.4. So that worked out quite nicely. So after 292.4 hours, we've got, there's my dog barking. After 292.4 hours, we have got left 25 becquerels of activity. Okay, and that is my final answer. All right, if I was using a different pen and not a glittery gel pen, I would highlight that answer, but unfortunately the highlighter won't mix well with my glittery gel pen. So that would be my final answer. Okay, perfectly acceptable for you to set it out like this. This is absolutely fine. Okay, so that's question 1. So question 2. I think I'm going to swap pens actually. There we go. Let's grab another highlighter. So phosphorus 32 has a half-life of 14.3 days. Important. If a sample of phosphorus 32 has an original activity of 750 becquerel, what will its activity be after 42.9 days? Okay, so it's, again, really similar to the first question. It's telling me that it starts on 750 BQ. So I'm going to start breaking that down in half. I'm going to start going across. So, do you know what? I don't even know what half of 750 is. This math is terrible, isn't it? 750 divided by 2 is 375. Half of 375 is 187.5. Half of that is 93.75. And half of that is complicated, 46.875. This is the problem when you pluck numbers out of thin air. So I'm going to stop there. I'm going to go through this and see what we get. So we've got 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Okay. So this first one, 14.3 days. The next one, 28.6 days. And then the next one, 42.9 days. Okay, so there we go. There's our final answer. So after 42.9 days, my activity is 93.75 becquerels. Okay, so there's my answer. Hopefully you can see that that makes sense and it's nice and straightforward. Okay, so those two are when you are given the half-life, you are given the original activity and told to look after a certain amount of time. Okay, this next question is we've got to work backwards to work out what the half-life is. All right, so let's have a little look at what we get. So after 42 days, the activity of a sample of phosphorus 32 has decreased from 400 becquerels to 50 becquerels. What is the half-life of phosphorus 32? Why have I left that question in? I just realised what I've done. And it's the same as question 2. How silly of me. Well, we already know the answer. However, I'm still going to do the question because at least then you can see how to calculate this, how to work this out. So after 42 days, it's decreased from 400 to 50. What is the half-life of phosphorus 32? Okay, so we're figuring out phosphorus. I didn't really need to highlight that. I just did it for the fun of it. So let's write out what our activity went from and to. So we're 400, 200, 100, 50. Okay, and this was after 42 days. Right, and this is 1 half-life, 2 half-lives, 3 half-lives. Okay, so 42 days over 3 half-lives. So all we need to do in this situation is just divide 42 by 3. Okay, because whatever 1 half-life is, if you times that by the number of half-lives it takes, then you'll get your final answer for like if you're working that way. But we're going to work backwards. So if it's 42 days, I'm going to divide that by 3. Well, it's 14. Okay. And then double check that it adds up. Obviously, 14 plus another 14, 28. Plus another 14, 42. Okay, so it does add up, it does make sense. So the half-life of phosphorus 32, 14 days. Obviously here I said it was 14.3. That's me being really technical. This is it, making it easier for the question. All right. But again, I know it's the same information as this question, but at least you can see how to do the 2 different examples. Right. I'm going to yawn, excuse me. Oh, I'm tired. Right. So the half-life of ruthenium-106 is 373.6 days. How about that? What was the original activity if it has an activity of 40 becquerels after 1,868 days? Okay, so this is 1 half-life, so we need to work out how many half-lives this is. So I'm going to do this ever so slightly differently. So we need to find out how many of these half-lives go into this number of days. So we're going to do 1868 divided by 373.6. Okay, so let's have a little look and do the maths. 868 divided by 373.3.6 even, and it's 5. So that is 5 half-lives, okay? So we're going to try and work backwards, and I'm going to try and do this as carefully as I can and as neatly as I can. So this is going to be 5 half-lives. So we're going to double that number. We're going to go backwards. So we've got 80. Ugh, I knew I was going to put my arrow in the wrong way. All right, full disclosure, there's a car outside. It might be my husband coming home from work, and if it does, the dog might go mad. So if the dog goes mad, I'm really sorry about the noise. I can just apologise. I'll keep doing the video though. So, so double that again. 160 becquerels, 3 half-lives, double that number again. 320. That's 2 half-lives. So we double it again. 640. I'm running out of space. I knew this would happen. 1 half-life there. Double that number again. 1,280. So the original activity, which is what we were looking for, the original activity is 1,280 becquerels. Okay. So all I've done there is I've worked backwards. So I've worked out how many half-lives, and then I've counted my number of half-lives backwards. Started at 40, because that's what it's finished on after this much time, and I've gone backwards, and I've got to there. Okay, hopefully that makes sense. I do think this is as straightforward as it gets doing these examples like this, and hopefully you're following it as you go through. There's, I think, 8 questions altogether. Yeah, 8 questions altogether. So we've got 4 more questions to do. All right, so stick with me. We'll see how we get on. So the half-life of indium-117 is 43.2 minutes. How many minutes are required for 75% of a sample to decay? So this is like a tricky one in the way it's worded, because it says they want, it's 43.2 minutes in a half-life. How many minutes are required for 75% of a sample to decay? If 75% of a sample is going to decay, that means there's only going to be 25% of it left. And that one will cause confusion, because you'll go, oh, 100, 75, that doesn't make sense. Okay, going from 100 to 75 doesn't make sense in a half-life, because you half it every time, because it's called half-life. So you go 100%, 50%, 25%. Okay, that's where you're going to link in the 75. All right, I'll just write it down just to show you what I mean. So we start with 100% of a sample. When you get given a percentage, it's when you're not given an actual real number for activity. So if you get given a percentage, it's in place of an activity. So it basically means you've got 100% of the activity, which doesn't make sense, but does make sense, if you get what I mean. So we go from 100% to 50% to 25%. Okay, if I've got 25% of something left, it means the 75% of it is gone. Please tell me you can do that maths, that 75 and 25 is 100. All right, so 100% to 25%. So it's got 2 half-lives, so 1 half-life, 2 half-lives. It's telling me that it's 43.2 minutes for 1 half-life. So 2 half-lives is 86.4 minutes. So my final answer for that one is 86.4 minutes. Okay. So that is just another example of how you can do this. All right. So 3 questions left. I don't think this is going too badly too far. Hopefully you'll be able, hopefully you'll be able to follow these quite easily. So last few questions. Let's have a little look. So again, here we go. We've got another question where it's talking about percentage rather than actual activity number. The half-life of astatine-210 is 8.1 hours. What percentage of a sample will remain after 40.5 hours? So let's go back. So half-life 8.1 hours. What percentage will remain after 40.5 hours? So I'm going to work out how many half-lives that is, so I know how many times I'm going to need to halve my activity. So 40.5 divided by 8.1 is 5. 5 again. So 5 half-lives. So I'm going to halve. I'm going to keep halving at 100. I'm going to halve it 5 times. Okay, so we're going to start with 100%. All right, I'm going to halve it. I'm going to get 50%. So that's 1 half-life. Going to halve it again. 25%. Okay, going to halve it again. 12.5%. Going to halve it again. And we're going to get 6.25%. We're going to halve it one last time for our 5th half-life, 3.125%. So that 3.125% is how much is going to be left after 40.5 hours. Okay, easy. I think it's easy anyway. Like, hopefully you guys will think it's easy. How inconvenient, I'm now being called by my husband, so it wasn't him coming through the front door. There we go. I have hung up on him. Right, last 2 questions, and then I'll have to ring him home. After ring him back, bless him. A rock once contained 4.0 milligrams of potassium-40, but now contains only 0.5 milligrams. Given that the half-life of plutonium-40 is 1.3 billion years, how old is the rock? Now, one of you did this question when it was written the other way and kind of got it a little bit wrong. It's about working. You've got to look at this number and know that you're halving this number. It's not about how many times 0.5 goes into 4. It's about how many times you've got to halve 4 to get to 0.5. Okay, so let's just write out the activity for this first. So we start off at 4 milligrams. This time it's oh, I better do my highlighting, hadn't I? Sorry, terrible. 4 milligrams. Now it contains 0.5. And it is 1.3 billion years old, 1.3 times 10 to the 9. Okay, so 4 milligrams, we're going to halve it, milligrams rather than becquerels, that's fine, doesn't really matter, it's still going to work out the same thing. So we go to 2.0 milligrams, then after another half-life, it becomes 1 milligram, and then after another half, it becomes 0.5. So we have got 1 half-life, 2 half-lives, 3 half-lives. So it is 3 half-lives to get from 4 to 0.5. So now we're going to do 3 times by 1.3 times 10 to the 9. So let's write that up here. So it's 3 half-lives times 1.3 times 10 to the 9. Put it in the calculator. 3 times 1.3 times 10 to the 9. And that is a horrible number in the calculator. That is 3.9 times 10 to the 9 years old. So that's basically 3.9 billion years old, which works. Okay. So again, slightly different approach to that question, but working out the number of half-lives and then multiplying it by a given age of a sample, I think that one's quite hard, but when you actually break it down into what it is that you've got to do, it's easy. It might just be me, but I think that's pretty straightforward. So let's have a little look. The half-life of tritium. Tritium is the name that we give to so hydrogen comes in 3 varieties. I've got a bit more space, so I'll just write this out. So hydrogen, you should know, looks like that. H is 1 and 1. H can also come as H2 and 1. That's called deuterium. And then we have 3 and 1. This is sometimes referred to as something called heavy water. if any of you go on to study chemistry at like A level or even degree level, which, you know, could be a possibility, you will look at heavy water in a little bit more detail, and then tritium as well. Tritium, sorry. Tritium's interesting. They're pretty cool. I always liked learning about them when I was at uni. But anyway, so tritium is hydrogen-3, and it's got a half-life of 12.3 years old. So they're saying if 64 milligrams of tritium is released from a nuclear power plant during the course of a mishap, hello Chernobyl, what mass of the sample will remain after 86.1 years? So we're going 86.1 years later. One half-life is 12.3 years. So one half-life is 12.3 years. We start with 64 milligrams, and after 86.1 years, it wants to know how much is going to be left. So let's work out how many half-lives this is, and then we can know how many times we need to half this 64. So 86.1 divided by 12.3 is, I really hope this isn't 5 again, because that'll just be silly, won't it? 7. So that's 7 half-lives. So let's break down 64 7 times. So 64 half is 32. 32 halved is 16. I'm just going to write my half-lives in actually, so we can keep track of what we're doing. It's good to write these in. I know it's a little bit repetitive, but it makes a difference. I think it keeps a nice routine. And I'm not saying you get extra marks for this in the exam, but if the examiner can see how you've really clearly laid this out and that you've got a process, then they'll know that, say if you get the wrong final answer, you might be able to get marks up here for an error carried forward, which is a possibility. You know, like if this was worth 4 marks and you got so much of it right and then just halved it ever so slightly wrong and then lost a mark, you can still get 3 marks for it. So it's so worth showing you're working out rather than just scribbling on a scrap piece of paper. You will have space to do this. Okay, so make sure that you do. Anyway, so that's 8, and then 4 half-lives. 4, half it again, 5 half-lives. 2, 6 half-lives is 1. 7 half-lives, 0.5. Nearly ran out of space. 0.5 milligrams. So after 86.1 years, we have got 0.5 milligrams left. And that will be my final answer. Okay, so hopefully from that you can see loads of different examples of questions and all the different ways that they can come up. And obviously they are really similar to the questions that you've been set. I've tried to make different elements and give different years and numbers and things, but they should help. That should help you do that. So yeah, have a watch this video. I know it's relatively long and I'm sorry I don't really stop to give you guys a chance to do it, but hopefully when you've watched this you can even put this on and do the worksheet at the same time. All right, so complete this worksheet. Make sure you've completed the other worksheet with the graphs on. I think that one is a lot easier. I will be around if anybody needs any help. And then the last thing that you've got to do is just a little set of exam questions, which is a little bit revision on the other lessons in radioactivity we've done as well. Next week, you've got 1 lesson on contamination, and then Friday's lesson is going to be a big revision session because you're actually going to do your end of topic test on this the following week. Okay, so good luck, watch, and let me know if you need anything.